So we saw in the last section that there are attractions between the molecules that kind of keep them together. And at very cold temperatures, the attractions can keep the molecules together in a solid phase. And as you increase the temperature, the attractions start to be partially broken. And we've got a liquid phase where the particles can kind of move over top of one another. They're still close together because the attractions are stronger than thermal energy, but they can be partially broken. And at very high temperatures, the thermal energy can completely overwhelm the intermolecular forces, and they can all break free and form gases. So the question is, what different intermolecular forces do we have? What attractions are there between the molecules? And so the first kind is the London dispersion force. So this is a kind of intermolecular force. I think it's probably worth defining what I mean by intermolecular force. So certainly in chemistry we call it a force. It's probably not really a force in the physics sense, but we're going to use that word anyway. So inter as opposed to intra, and intra means inside of, and inter means sort of in between. So if I take a molecule like hydrogen chloride, and I have, say, two molecules of hydrogen chloride, we know that there's a covalent bond between the two atoms right here. And this is referred to as an intramolecular force. So it is inside of the molecule. So intramolecular force. Right, and this is what we call a covalent bond. Okay, so we're not breaking these bonds here. We need extremely high temperatures to break these bonds, so thousands of degrees, and we can break those. So normally we're not breaking the forces in between the atoms inside of the molecules. Instead, we're breaking the forces in between the molecules. So in red here, I'm going to draw these in dashes. That's typically our sort of indication it's not as strong as a bond, let's say. This is our intermolecular force. So intermolecular force, and we'll typically just abbreviate that as IMF from now on. Yes, I know intra and inter start with the same letter, but IMF is typically always kept for these forces of attractions between the individual molecules themselves. So the first kind we have is the London dispersion force. London is actually after the fellow who first sort of described it, Fritz London. Unfortunately, it's not after the capital of England. I'm sorry about that. So the coolest thing about the London dispersion force is that it is present between all molecules. So oftentimes on the exam, right, we'll ask you to list the intermolecular forces. Well, you always can write London down. That's always a given. And it's actually proportional to the number of electrons in the molecule. So I suppose if your molecule didn't have an electron, technically it wouldn't have a London dispersion force. So a proton probably doesn't actually have a London dispersion force, but everything else will. So it's proportional to the number of electrons. We'll see later on that counting electrons is kind of a pain, so we normally just assume it's proportional to the molecular weight. So the larger molecules are, typically the more electrons they have. It's also proportional to the surface area of the molecule. So we're going to see that this is an effect that's very sort of close range, and the more surface you've got, right, the more attraction, the more sticky this is going to be. The smaller your surface area of your molecule, the less important this force is going to be.